Imagine a world where reality is not fixed, where particles can be in two places at once, and where your very observation shapes the universe. Tonight, we'll drift through the mysteries of quantum physics, exploring how the tiniest building blocks of reality challenge everything we thought we knew. Welcome to Sleep Entangled, where science meets serenity. If you love quantum mysteries, consciousness, and meditative explorations, hit subscribe and join this gentle journey through the universe. Chapter 1: Quantum Beginnings. Imagine for a moment a world where the very fabric of reality is not fixed, where certainty is an illusion, and where the tiniest building blocks of the universe behave in ways that challenge everything we thought we knew. Tonight, we will drift together into this mysterious landscape of quantum physics, a realm where particles can exist in multiple places at once. Light can behave as both a wave and a particle, and observation itself subtly shapes reality. Welcome to Sleep Entangled, where the mysteries of science are woven into calm, meditative explorations designed to relax your mind and expand your imagination. If you enjoy gentle journeys through consciousness, quantum reality, and the poetic nature of existence, consider subscribing now so we can explore these infinite possibilities together. Let us begin by stepping softly into the early 20th century, a time when the universe was about to reveal secrets that would overturn centuries of classical understanding. In that era, physics was governed by certainty. Newton's laws described the motion of planets, projectiles, and falling apples with astonishing precision. Maxwell's equations explained the behavior of light and electromagnetism. The universe seemed to follow a predictable clockwork rhythm, a cosmic ballet that could be understood, measured, and anticipated. Yet, beneath this reassuring surface, subtle anomalies began to appear, hints that reality was far more playful and mysterious than anyone had imagined. One of the first cracks in classical certainty appeared through the work of Max Planck, a German physicist whose mind danced along the edges of the known. In 1900, Planck introduced the idea that energy is not a smooth, continuous stream, as previously thought, but comes in discrete packets called quanta. He arrived at this idea while studying the mysterious ultraviolet catastrophe, a problem that classical physics could not solve. A black body, a theoretical perfect emitter of radiation, should release infinite energy at short wavelengths. The mathematics failed, and the universe seemed to whisper a subtle question. Perhaps energy flows not as a river, but as a series of tiny, purposeful drops. Each quantum, like a delicate droplet of possibility, carried potential, and in recognizing this, Planck planted the seeds of a revolution. Soon, another quiet yet profound shift arrived in the hands of Albert Einstein, who in 1905 extended Planck's idea to light itself. Einstein proposed that light, which had been long understood as a continuous wave, also behaves as a particle, a discrete unit of energy called a photon. This insight came from his explanation of the photoelectric effect, a phenomenon where electrons are ejected from metal surfaces when illuminated by light. Einstein observed that the effect depends not on the intensity of light, but on its frequency, revealing a subtle, almost poetic duality in nature. Light can ripple across space like a wave, yet deliver its energy in precise quantized bursts like particles. This duality challenged centuries of classical thinking, showing that even the most familiar aspects of the universe harbor hidden complexity. By now, the universe was revealing itself as a playful puzzle. Imagine electrons orbiting their atomic nucleus, like miniature planets, yet refusing to follow the rules of classical physics, skipping between energy levels, emitting light in discrete bursts, and existing in multiple possibilities until measured. This was not merely theoretical, it was observable in experiments, calculations, and the gentle hum of scientific curiosity. Niels Bohr formalized this understanding with his Bohr model of the atom, where electrons inhabit discrete energy levels and transition between them by absorbing or emitting quanta of light. Bohr's vision was both precise and poetic, suggesting that reality itself is structured as a dance of probabilities, a universe in which certainty is a delicate and fleeting companion. At the same time, Werner Heisenberg and Erwin Schrödinger were giving form to this new realm. Heisenberg introduced matrix mechanics, a framework focusing on what can be observed rather than hidden paths, while Schrödinger's wave mechanics described the state of a particle as a wave function, symbolized by psi. These wave functions are not mere abstractions. They are clouds of probability, reflecting the multiple potential states a particle may occupy until observations occurs. Imagine a cat in a box, both alive and not alive, or an electron simultaneously occupying countless positions. Quantum mechanics invites us to suspend rigid certainty and embrace a universe that thrives in multiplicity. Einstein, however, was uneasy. He longed for a reality independent of observation, famously declaring, "God does not play dice." He wrestled with the idea that the universe could be fundamentally probabilistic, a place where outcomes are not predetermined but emerge from a subtle web of possibilities. Bohr, representing the Copenhagen interpretation, gently countered that reality and observation are intertwined. What we measure defines what exists, not as an imposition of human will, but as an intrinsic feature of the quantum world. The universe is participatory, a stage where observer and observed dance in mutual influence. Consider for a moment the poetic imagery of these early discoveries. Quanta ripple through space. Photons arrive like tiny messengers of energy. Electrons hover in clouds of potential, and each measurement is a gentle nudge, collapsing a cloud of possibilities us into a single reality. The early pioneers of quantum physics were learning to read this intricate language, discovering that beneath the surface of certainty lies a universe rich in probability, beauty, and subtle complexity. Even as we reflect softly on these ideas, notice how the metaphors extend beyond physics. The uncertainty and multiplicity of quantum beginnings mirror the flow of consciousness itself. Thoughts flicker like electrons, choices branch like quanta, and moments of awareness collapse infinite potential into lived experience. Quantum physics, in this sense, is both science and meditation, a gentle reminder that mystery is not a problem to solve, but a landscape to explore. Planck, Einstein, Bohr, Heisenberg, and Schrödinger each contributed their own verse to the quiet poetry of quantum physics. Together, they revealed a world that is at once playful, precise, and deeply mysterious. By understanding this early chapter, we prepare ourselves for the wondrous journey ahead, exploring wave-particle duality, superposition, entanglement, and the quantum foundations of reality, all while relaxing gently into the rhythm of thought and breath. Before we drift further, a soft reminder. If you enjoy these gentle journeys into quantum mystery, consciousness, and the nature of reality, consider subscribing to Sleep Entangled. By joining this community, you support the creation of meditative, scientifically rich explorations designed to help you relax, reflect, and drift peacefully into sleep. Chapter 2: Wave-Particle Duality. Imagine holding a photon in your hand, not physically, of course, but in thought, like cradling a tiny ripple of possibility. You might expect it to behave predictably, like a marble rolling across a table. Yet in the strange, beautiful world of quantum physics, this photon is a dual citizen, part particle, part wave. It carries the elegance of a ripple on water and the discrete precision of a pebble at the same time. This is the heart of wave-particle duality, a concept that invites us to see reality not as fixed and solid, but as fluid, interconnected, and wonderfully paradoxical. The journey begins with the double-slit experiment, one of the most famous and mesmerizing experiments in physics. Picture a beam of light or electrons traveling toward a barrier with two narrow slits. If you observe which slit the particle goes through, it behaves like a particle, choosing a path, arriving at a screen behind the barrier in a predictable pattern. But if you refrain from observing, allowing the particle to pass freely, it creates an interference pattern, as if it were a wave traveling through both slits simultaneously, overlapping, merging, and producing a delicate ripple of possibilities. This is not a trick or illusion. This is reality itself, revealing its probabilistic nature. What does this mean for our understanding of the universe? It tells us that the act of observation is participatory. By simply observing, by interacting with the quantum system, we collapse its cloud of possibilities into a single, tangible outcome. Reality, in this sense, it is not entirely independent of us. It is co-created in the delicate interplay between observer and observed. Imagine gently placing your finger on a calm pond. The ripples you create are real, not imposed but emergent, shaping the water's surface. In the quantum world, our observations are like these ripples, shaping reality in subtle yet profound ways. The dual nature of light was first illuminated by Albert Einstein, whose explanation of the photoelectric effect revealed that light can eject electrons from metal surfaces depending on its frequency. This discovery confirmed that light is not merely a continuous wave. It is also made of discrete photons, each carrying a quantum of energy. Here, the universe whispers a gentle paradox. Something can be both continuous and discrete, flowing and punctuated, wave and particle, at once. But light is only the beginning. As the decades passed, physicists discovered that electrons, atoms, and even large molecules exhibit similar duality. Schrödinger's electron waves are not just mathematical abstractions. They represent real, measurable probabilities, shimmering like a mist around the nucleus. Each electron is a ghostly possibility, a tiny cloud of potential until observed. And when we measure it, the wave function collapses, revealing a single, concrete reality. This wave-particle duality challenges our classical notions of certainty. In everyday life, objects appear solid and determinate. A chair is always a chair. A coin is always heads or tails. Yet at the quantum scale, certainty dissolves into probability, and the universe becomes a dance of possibilities. Schrödinger's famous cat thought experiment poetically captures this. A cat in a box is simultaneously alive and dead until the box is opened and observation occurs. While we do not encounter such paradoxes in our daily lives, the principle invites reflection. Our world may be shaped by observation, probability, and potential, even if subtly. Wave-particle duality is also the foundation for modern technology. Quantum computing, for instance, leverages this principle to allow qubits to exist in superposition, simultaneously representing multiple states. Unlike classical bits, which are either 0 or 1, qubits can explore a vast landscape of possibilities, enabling calculations that classical computers struggle to perform. This duality is not just theoretical, it has practical consequences, powering advances in chemistry, optimization, and secure communication. Another fascinating aspect of wave-particle duality is its connection to quantum interference. When particles interfere like waves, they create patterns of constructive and destructive interference, where possibilities amplify or cancel each other out. It's a subtle reminder that quantum reality is relational. The outcome of one particle can be influenced by the potential of others, even when separated by vast distances. This leads naturally into quantum entanglement, a phenomenon we will explore in later chapters, where particles maintain instantaneous connections across space, defying classical expectations. To appreciate this fully, imagine a cosmic dance floor. Each particle, each photon, moves not alone, but in relationship with the entire universe of possibilities. Their behavior is shaped by both local interactions and the broader quantum context. When we observe, we join the dance, gently guiding outcomes, yet never fully controlling the rhythm. Wave-particle duality invites us to embrace uncertainty, recognizing that flexibility, openness, and curiosity are fundamental to understanding reality. The philosophical implications are profound. Wave-particle duality suggests that certainty is not the default state of the universe, and that our perception is always intertwined with what exists. We are not passive spectators, but participants in the unfolding of reality. Even in meditation or gentle reflection, this principle can inspire humility and wonder. We observe, we interact, and the universe responds, revealing patterns and outcomes that are neither fixed nor entirely random. Let's pause for a soft visualization. Imagine electrons shimmering around an invisible nucleus, like tiny, delicate fireflies, their paths undefined, their locations a mist of probability. Some photons ripple like gentle waves across space, others impact like precise glowing beads. Every interaction, every observation, nudges the cloud of possibilities into a single, elegant reality. In this gentle image, quantum mechanics feels not just like science, but like poetry, a meditative exploration of existence itself. Wave-particle duality also reminds us that observation is a creative act. Just as an artist's brushstroke brings a painting into being, so does the act of measurement bring one of many quantum possibilities into our tangible experience. This principle stretches beyond physics, touching consciousness, choice, and the subtle ways we influence our environment. Reality, it seems, is both discovered and co-created, an interplay between what exists independently and what emerges through interaction. Historically, the recognition of wave-particle duality led to a rethinking of energy, matter, and light. It inspired generations of physicists to explore the limits of knowledge, the boundaries between certainty and probability, and the profound mystery of existence itself. From Planck's quanta to Einstein's photons, from Bohr's electrons to Schrödinger's wave functions, the quantum world is revealed as fluid, relational, and full of gentle surprises. Even as we drift through these concepts, notice how this knowledge invites calm reflection. Quantum duality is a reminder that uncertainty is not frightening, but liberating, that multiple possibilities can exist simultaneously, and that observation, whether scientific, meditative, or conscious, is a gentle act of participation in the universe's unfolding. Finally, before we move deeper into the quantum landscape, a soft reminder. If you enjoy exploring the poetic mysteries of reality, consciousness, and quantum physics while easing into relaxation and meditative reflection, consider subscribing to Sleep Entangled. Your presence supports these journeys and helps create more content where science meets serenity. Chapter 3: Schrödinger's Equation, Superposition, and Quantum Probability. Imagine a universe where every particle carries within it a cloud of infinite possibilities, a soft haze of potential outcomes, like mist rolling gently over a valley at dawn. This is the world described by Schrödinger's equation, a cornerstone of quantum mechanics that reveals how particles exist not in a single state, but as a superposition of all possible states until observed. Tonight, we will drift into this elegant, mysterious realm, exploring the subtle laws that govern the microscopic universe, and perhaps the very fabric of existence itself. At the heart of this chapter lies the concept of the wave function, symbolized by the Greek letter E psi. The wave function is not merely an equation. It is a map of probabilities, a mathematical representation of all the potential states a quantum system can occupy. Think of it as a gentle cloud of possibilities, each point within the cloud representing a potential location or energy state of a particle. Until we measure, observe, or interact with the system, all these possibilities coexist, overlapping like layers of sound in a delicate symphony. Erwin Schrödinger, an Austrian physicist with a mind both precise and imaginative, formulated this wave equation in 1926. Unlike classical physics, which seeks definite paths and exact outcomes, Schrödinger's approach embraces uncertainty and potentiality. The equation predicts how the wave function evolves over time, allowing physicists to calculate the likelihood of finding a particle in a given state. Yet it does not tell us exactly what we will observe, only the probabilities. This subtle distinction is the heart of quantum mechanics. Certainty is replaced by a landscape of possibility. To understand superposition, consider the poetic image of a gentle ripple across a pond. Toss two stones simultaneously into the water, and the ripples overlap, interfere, and merge. No single wave dominates until you observe, until your gaze meets the water's surface. In the quantum realm, particles behave similarly. An electron is not merely here or there. It exists in a blend of states, a delicate interference of possibilities. When measured, the wave function collapses, and a single concrete outcome emerges. This principle can be vividly illustrated through Schrödinger's famous thought experiment, the cat in the box. Picture a cat, a tiny vial of poison, and a quantum mechanism triggered by the decay of an unstable atom. Until the box is opened and observation occurs, the cat is both alive and dead, a simultaneous embodiment of superposed states. While no one intends to harm an actual cat, The thought experiment elegantly captures the mystery of quantum superposition and the paradoxical nature of observation. Reality, it suggests, is not fixed but participatory, shaped in part by the act of perceiving. Superposition is not merely a philosophical curiosity, it has tangible, practical implications. In the world of quantum computing, superposition allows qubits to represent multiple states simultaneously. Unlike classical bits, which are either 0 or 1, qubits can exist in combinations of 0 and 1 at the same time, exploring vast landscapes of possibility. This capability enables computations that are exponentially faster than classical systems for certain problems, from complex optimization tasks to simulating quantum chemistry. In this sense, superposition is both a theoretical marvel and a tool of immense practical power. Another critical element of this quantum landscape is Heisenberg's uncertainty principle, a gentle reminder that some aspects of nature are inherently unknowable with perfect precision. The principle states that the more precisely we know a particle's position, the less precisely we can know its momentum, and vice versa. This is not a limitation of measurement instruments, but a fundamental feature of reality itself. Particles exist in fuzzy probabilistic clouds where precise knowledge of one property naturally blurs another. The universe whispers through these uncertainties, inviting patience and humility and wonder. To visualize this, imagine a glowing mist in a forest at twilight. You can see its shape with clarity in one area, but as you focus, other regions fade into obscurity. Similarly, in the quantum world, particles occupy regions of probability, their properties delicately balanced between possibility and actuality. The act of measurement, the gentle attention of observation, nudges these probabilities into a concrete outcome, just as sunlight highlights patches of mist, revealing fleeting clarity amid the unknown. Superposition also provides a gateway to quantum tunneling, a phenomenon where particles pass through barriers that classical physics would deem impenetrable. Imagine a tiny ball rolling up a hill. Classically, if it lacks sufficient energy, it cannot reach the other side. Yet at the quantum scale, particles sometimes tunnel through energy barriers, appearing on the other side without following a classical path. This seemingly magical behavior underpins processes like nuclear fusion in stars, where hydrogen nuclei overcome electrostatic repulsion, powering the sun and all life on Earth. Decoherence is another essential concept to explore gently, especially for our meditative contemplation. Decoherence occurs when a quantum system interacts with its environment, causing superposition states to collapse into classical behavior. It explains why we do not see macroscopic objects in superpositions. They are constantly interacting with countless environmental factors. Yet even in this collapse, there is beauty. Decoherence reveals the fragile boundary between quantum possibility and classical reality, highlighting the intricate balance that sustains the universe. Quantum probability also invites us to reconsider our role as observers. In classical physics, the universe exists independently of our perception. In quantum mechanics, observation is intertwined with reality, a subtle dance in which awareness guides outcomes. This is not mystical, but an empirical feature observed in countless experiments. Even the simple act of deciding which experiment to perform shapes the probabilities that nature will reveal. Imagine gently touching a violin string. Your fingers guide the vibrations, creating resonance, shaping music that existed in potential before your touch. So too, consciousness interacts with the quantum world, collapsing clouds of probability into tangible experience. Philosophically, superposition and probability suggest a universe rich in possibility and wonder. Life, consciousness, and reality itself may be more fluid than rigid. The quantum world teaches that multiple futures coexist until attention collapses them into a single path. This awareness can transform how we perceive daily life. Choices, thoughts, and actions are not merely linear, but participate in the broader tapestry of existence, echoing the interconnectedness of all things. Let us also gently reflect on Schrödinger's wave equation itself. Mathematically elegant, it describes how quantum systems evolve over time. Each solution is a cloud of probabilities, a dynamic, undulating structure, alive with potential. This framework allows physicists to predict outcomes statistically, even when individual events remain uncertain. It is a poetic testament to the universe's subtlety. We can know the probabilities, yet the precise outcome remains a quiet mystery until observed. Even at a macroscopic scale, the principles of superposition and probability resonate. Think of your thoughts drifting before sleep, each possibility a delicate path, each decision a gentle collapse of potential into lived experience. Quantum mechanics, in this meditative reflection, mirrors consciousness itself, ever-changing, intertwined with observation, rich in subtlety. Finally, as we gently draw this chapter to a close, take a moment to breathe deeply, imagining a universe alive with clouds of potential, particles shimmering in waves of possibility, and observation guiding the unfolding of reality. The beauty of Schrödinger's equation is that it invites both scientific understanding and poetic reflection, a bridge between knowledge and wonder, between calculation and meditation. If you are enjoying this gentle exploration of quantum probability, superposition, and the foundations of reality, consider subscribing to Sleep Entangled. Your presence supports the creation of immersive, meditative journeys where science meets serenity, allowing us to explore the mysterious universe together. Chapter 4: Quantum Entanglement, Decoherence, and Interconnectedness. Imagine two particles born together in the heart of a star or a delicate laboratory experiment, drifting apart across the universe. Despite the vast distance, a whisper of connection remains, a subtle, instantaneous correlation that transcends space and time. This is quantum entanglement, one of the most enchanting and puzzling phenomena of quantum physics. It suggests that reality is not merely a collection of independent objects, but a woven tapestry of interconnectedness, where the state of one particle reflects the state of another, even across cosmic expanses. Entanglement was first noticed in thought experiments and refined through theory, famously highlighted in the Einstein-Podolsky-Rosen paradox. Einstein himself called it spooky action at a distance because it seemed to defy the limitations of space, time, and information transfer. Yet experiments have repeatedly confirmed that entangled particles share correlations that cannot be explained by classical physics. When one particle is measured, its partner instantaneously reflects complementary properties, as if the universe gently synchronizes them, whispering secrets across light years. To visualize this, imagine holding two tiny lanterns in separate rooms, yet the glow of one always mirrors the other, even without any wires or signals connecting them. In the quantum realm, the particles themselves exist in superposition until observed, meaning their states are not fixed independently. The measurement of one collapses the probabilities, instantly informing the other. This subtle dance challenges our classical notions of locality and causality, inviting us to see connection as fundamental to reality itself. Entanglement is not just theoretical, it is at the heart of quantum technologies. Quantum teleportation, for instance, leverages entangled particles to transmit information instantaneously without moving matter in the classical sense. Secure communication methods exploit entanglement's fragility. Any attempt at eavesdropping disturbs the system, revealing intrusion. In these applications, the strange principles of quantum physics translate into practical tools, turning mystery into utility. Yet entanglement is deeply fragile. This fragility introduces the concept of decoherence, which we touched upon in the previous chapter. Decoherence occurs when a quantum system interacts with its environment, collapsing superpositions and breaking the entangled correlations. Imagine a delicate soap bubble drifting in the air. The gentlest touch, a breath of wind, or even a stray photon can disrupt its form, causing it to vanish. Quantum systems are similarly sensitive. Maintaining entanglement over long distances or for complex systems requires careful isolation and cooling to near absolute zero, highlighting the delicate, ephemeral beauty of quantum states. Decoherence also explains why the macroscopic world feels solid and deterministic, while individual particles dance in superpositions, interacting and collapsing unpredictably. The enormous number of particles in objects we see every day averages out these uncertainties. The gentle blur of probability becomes the familiar solidity of chairs, trees, and stars. Yet at the microscopic level, reality remains a fluid landscape of potential, interconnected by subtle quantum threads. The interplay of entanglement and decoherence invites a broader reflection. Interconnectedness is not merely theoretical, but a structural property of the universe. Particles do not exist in isolation. They respond to and are influenced by one another across space and time. This perspective can be mirrored in consciousness and life itself. Consider how humans, animals, and ecosystems interact. Actions, thoughts, and events ripple outward, influencing distant systems in ways we may not immediately perceive. Just as entangled particles maintain correlations across space, our lives are entangled with the environment, society, and the cosmos, subtly and profoundly. Entanglement also has poetic parallels in everyday experience. Have you ever felt an intuition about someone far away, or a sudden understanding that bridges moments separated by time? While classical physics may struggle to explain such experiences, quantum principles remind us that connection can be instantaneous, subtle, and unobservable, yet undeniably real. In this sense, quantum entanglement becomes both a scientific and meditative metaphor. Reality is a web of relationships, delicate yet resilient, where every observation, choice, and action reverberates. The implications for consciousness are equally fascinating. Some theories suggest that observation and awareness might themselves be entangled with the systems we perceive. This does not mean consciousness magically controls the universe, but that the act of observing, reflecting, and participating interacts with reality at a fundamental level. Imagine gazing at a calm lake. Your attention causes subtle ripples, interacts with the water's natural patterns, and transforms perception. At the quantum scale, this interplay becomes mathematically precise, revealing a universe that responds to measurement and interaction. Now, let's gently explore the practical world again. Quantum entanglement is foundational to quantum computing and cryptography. In a quantum computer, entangled qubits allow for simultaneous exploration of multiple computational paths, dramatically increasing efficiency for certain complex problems. Quantum cryptography uses entangled particles to secure communication. Any attempt to observe the particles alters their states, providing an immediate signal of interference. In these ways, entanglement becomes not just a theoretical curiosity, but a cornerstone of emerging technologies, reshaping how we compute, communicate, and interact with information. Entanglement also resonates with the philosophical concept of non-locality, the idea that reality is not confined to separate points in space. The universe, at its deepest level, appears holistic, integrated, and relational. Particles influence one another instantaneously, and the universe behaves less like a collection of independent objects and more like an interconnected network of possibilities. This perspective gently shifts how we think about ourselves, our lives, and our place in the cosmos. We are not isolated observers, but participants in a vast, entangled web of existence. Returning to decoherence, notice how delicate quantum systems are to the surrounding environment. Every interaction, light, heat, vibration, nudges particles into classical states. This teaches a subtle lesson for life. Context, environment, and interaction shape outcomes. Just as decoherence transitions quantum possibilities into classical reality, our environment influences thoughts, habits, and perceptions. By cultivating awareness and gentle attention, we can navigate both microscopic and personal realities with grace and intentionality. Finally, let us meditate on the poetic beauty of entanglement. Imagine two photons drifting across galaxies, forever connected, carrying subtle correlations that bridge unimaginable distances. Imagine your awareness softly observing, participating, and resonating with this cosmic web. Every gentle breath, every conscious reflection echoes in the universe, subtly shaping the unfolding tapestry of reality. In this sense, quantum entanglement is not just physics. It is an invitation to see the universe as alive, relational, and intertwined. Before we close this chapter, a quiet reminder. If you enjoy exploring the mysteries of quantum physics, consciousness, and the subtle dance of reality, consider subscribing to Sleep Entangled. By joining this meditative journey, you support immersive, soothing explorations where science meets serenity, allowing us to uncover the poetic truths of the universe together. Chapter 5: Quantum Tunneling, the Quantum Vacuum, and the Active Universe. As we continue our journey into the gentle mysteries of quantum physics, let us imagine a universe that is not static, not solid, but a vibrant, living canvas of possibilities. In this chapter, we explore two fascinating concepts: quantum tunneling, where particles traverse barriers that classical physics deems impossible, and the quantum vacuum, a seemingly empty space teeming with energy, potential, and subtle fluctuations. Together, these phenomena reveal a universe that is not merely observed, but actively participating in its own unfolding. Quantum tunneling is a phenomenon that can feel almost magical. Imagine a ball rolling toward a hill. Classically, if it does not have enough energy, it cannot reach the other side. Yet, in the quantum world, a particle can appear on the other side of a barrier, as if it had passed through the wall itself. This defiance of classical expectation is not fantasy. It is observed in laboratories worldwide. Electrons, for instance, routinely tunnel through thin barriers, enabling devices like tunnel diodes and the scanning tunneling microscope, which allows us to image surfaces at atomic resolution. The implications of tunneling extend far beyond electronics. In the cores of stars, nuclear fusion occurs because hydrogen nuclei can overcome electrostatic repulsion through quantum tunneling. Without this phenomenon, stars could not ignite, and the warmth and light of the cosmos would be absent. Tunneling is not merely an abstract curiosity. It is a foundational process sustaining life itself, a silent choreography of probabilities that powers the universe. To visualize tunneling, imagine a ghostly bridge appearing between two cliffs, allowing travelers to cross effortlessly, even when classical paths are blocked. Particles behave similarly, exploring possibilities that classical physics would forbid, revealing the universe's inherent creativity. This is a universe that does not adhere rigidly to deterministic rules, but allows flexibility, spontaneity, and novelty. Beyond tunneling lies the quantum vacuum, which might initially seem empty, a void of nothingness. Yet physics reveals that this vacuum is anything but empty. It is alive with fluctuations, energy, and virtual particles that pop in and out of existence, influencing reality in subtle ways. Even nothing is dynamic, vibrant, and structured, reminding us that the absence of matter does not imply the absence of potential. These virtual particles, fleeting and elusive, produce measurable effects such as the Casimir effect, where two metal plates placed extremely close together in a vacuum experience a tiny attractive force. This arises not from the plates themselves, but from the underlying sea of quantum fluctuations. The universe, even in its apparent emptiness, sings with energy, possibilities, and gentle interactions that we can detect if we look closely enough. The quantum vacuum also carries profound implications for cosmology and the structure of reality. The very fabric of space may be shaped by these fluctuations, suggesting that space itself participates in the evolution of the universe. In this sense, the vacuum is not a passive stage, but an active participant in the unfolding of cosmic events. Galaxies, stars, and particles emerge and interact against this subtle, dynamic backdrop, which shapes probabilities and influences outcomes in ways we are only beginning to understand. Consider the wave function collapse, which we explored in the previous chapter. The vacuum plays a subtle role here, providing the field in which particles exist and evolve. When a particle is observed, the wave function collapses, and a definite outcome manifests. But this collapse occurs within the active quantum vacuum, a space alive with potential and subtle interactions. Reality, therefore, is not a fixed stage. It is a responsive, participatory arena, shaped by the interplay between matter, energy, and observation. Quantum tunneling also introduces the idea that boundaries are more fluid than they appear. Particles can cross seemingly impossible obstacles, suggesting that restrictions at the quantum level are probabilistic, not absolute. This resonates poetically. In our own lives, boundaries may be more permeable than they appear. Just as particles navigate barriers through subtle probabilistic paths, our thoughts, choices, and actions may create pathways in life that are not immediately obvious, but rich with potential. The interplay of tunneling and the quantum vacuum also illuminates the concept of quantum fields. Instead of thinking of particles as isolated solid objects, quantum field theory proposes that particles are excitations within underlying fields, much like waves rising in a vast ocean. The electron is a ripple in its field, photons are ripples in the electromagnetic field, and all matter and forces emerge from these dynamic interactions. Reality, therefore, is not composed of isolated entities, but of vibrating interconnected fields, each influencing the others in subtle, intricate ways. These fields do not exist passively. They are active, dynamic, and relational, constantly interacting to shape the properties of particles, the structure of atoms, and the behavior of forces. The Higgs field, for instance, endows particles with mass, providing the medium through which matter experiences resistance and weight. Without this field, the universe would be profoundly different. Particles would float weightlessly, and stars, planets, and life would struggle to form. Here, the quantum vacuum and fields together sculpt the very fabric of existence, orchestrating the dance of matter and the energy. Quantum tunneling and the vacuum also provide a glimpse into the probabilistic nature of reality. At the microscopic scale, outcomes are not predetermined. They emerge from a web of possibilities, influenced by interactions with the surrounding fields. This embraces uncertainty, replacing rigid determinism with a gentle acceptance of unpredictability. It is a universe where novelty and surprise are not errors, but essential features. A playground for probabilities that manifest in ways both subtle and profound. To bring this closer to a meditative reflection, imagine a gentle stream weaving around stones, creating ripples that interact, merge, and dissipate. Particles and fields must behave similarly, exploring possibilities, interacting with one another, and creating patterns of energy and matter that shape reality. Observation, measurement, and interaction collapse some of these possibilities into actuality, but the underlying quantum vacuum continues to hum, alive with potential. Finally, consider the poetic resonance of these ideas. Tunneling reminds us that boundaries are flexible, that possibilities can emerge from unlikely paths. The quantum vacuum teaches us that even apparent emptiness is full of energy, potential, and subtle influence. Together, they invite us to see the universe as alive, participatory, and interconnected, a realm where observation, action, and subtle forces dance in harmony to shape reality. As we draw this chapter to a gentle close, take a deep, slow breath, imagining particles navigating barriers with grace, virtual fluctuations whispering across the vacuum, and fields vibrating softly throughout space. Reality is not static, it is dynamic, playful, and full of possibility. Let this reflection settle as you exhale, feeling the subtle rhythm of the quantum universe echoing within your own awareness. If you have enjoyed this immersive journey into quantum tunneling, the active vacuum, and the subtle energy of the universe, consider subscribing to Sleep Entangled. By joining this journey, you support explorations where science meets serenity, allowing us to gently uncover the poetic and profound mysteries of existence together. Chapter 6: Quantum Interpretations, Copenhagen, Many Worlds, and the Role of Observation. As we continue our journey through the quantum landscape, let us pause to reflect on one of the most profound questions in physics. What does reality truly mean at the quantum level? The phenomena we have explored, superposition, entanglement, tunneling, and the active vacuum, all challenge classical notions of certainty and objectivity. But to interpret these wonders, physicists have developed frameworks that attempt to explain how observation and reality intertwine. Two of the most famous frameworks are the Copenhagen interpretation and the many worlds interpretation. The Copenhagen interpretation, formulated in the early 20th century by Niels Bohr and Werner Heisenberg, proposes that a quantum system remains in a superposition of possibilities until it is observed. In this view, reality does not have a definite state independent of measurement. The famous wave function, represented mathematically by the symbol psi, encodes all possible outcomes, and observation collapses it into a single, definite reality. To visualize this, imagine a delicate mist hovering in a quiet forest at dawn. Each droplet represents a potential outcome, shimmering in the early light. Only when you step into the mist and touch it does a path solidify beneath your feet, defining one trajectory among countless possibilities. Similarly, in the Copenhagen interpretation, observation is an active participant, bringing one of many potential realities into existence. This interpretation elegantly explains phenomena such as the double-slit experiment. Photons or electrons fired at two slits create an interference pattern, behaving like waves when unobserved. Yet when a detector is placed, the particles behave like discrete points. In the Copenhagen view, the act of measurement forces reality to choose a definite outcome, highlighting the essential role of the observer. Albert Einstein, however, famously objected. He believed in an objective reality that exists independently of observation, famously saying, "I like to think the moon is there even if I am not looking at it." Einstein's discomfort reflects a deeper philosophical tension. Does the universe exist independently of us, or is observation inseparable from existence itself? The Copenhagen interpretation leans toward the latter, inviting us to consider reality as a participatory, dynamic process rather than a static backdrop. In contrast, the many worlds interpretation, proposed by Hugh Everett III in 1957, offers a different vision. Rather than collapsing possibilities into a single outcome, many worlds suggest that all possible outcomes occur simultaneously, each in its own branching universe. Every time a quantum event has multiple potential results, the universe splits, creating parallel realities where each outcome is realized. Imagine standing at a crossroads. At each turn, a new path appears, and you step onto one, but other versions of yourself step onto the other paths, exploring different possibilities. In the many worlds view, reality is not singular, but a vast, branching multiverse, where every choice and every quantum event generates countless alternative realities. Both interpretations grapple with the role of the observer, but in strikingly different ways. Copenhagen emphasizes measurement as the mechanism that selects one outcome from many, while many worlds removes the need for collapse, proposing that all outcomes coexist in a sprawling, invisible network of realities. Each perspective offers unique philosophical and practical insights, shaping how we understand observation, probability, and existence itself. Quantum mechanics also introduces a deeper layer, the relationship between observation and knowledge. The act of measurement does more than merely reveal a pre-existing property. It actively defines the reality being observed. This challenges our classical intuition, where objects exist with fixed properties, independent of perception. In the quantum realm, observation and reality are entangled in a subtle dance, like a waltz, where each step both reveals and shapes the music. The many worlds interpretation also redefines probability. In classical terms, we assign odds to different outcomes, but in a multiverse, probability is not about which outcome will occur. It is about how many versions of ourselves experience each outcome. The universe does not choose, it realizes all possibilities, and our subjective experience is one thread in an infinite tapestry of outcomes. This perspective encourages a gentle, meditative reflection. Each choice we make unfolds countless parallel realities, and our awareness is part of this vast quantum network. To bring this closer to our everyday experience, imagine flipping a coin. Classically, it lands either heads or tails. In Copenhagen, the coin is in a liminal state, both heads and tails, until someone looks, forcing one reality to manifest. In many worlds, the coin lands heads in one branch of reality and tails in another, creating parallel universes where each outcome is realized. Both views challenge our intuition, inviting us to embrace uncertainty and complexity. These interpretations also shed light on quantum decoherence, which we explored in previous chapters. Decoherence occurs when a quantum system interacts with its environment, causing superpositions to appear to collapse and giving rise to classical reality. In the Copenhagen interpretation, decoherence supports the idea of collapse, while in many worlds, it explains why branches become effectively independent, creating distinct realities that no longer interfere with each other. Beyond thought experiments and philosophical musings, these interpretations influence emerging technologies and research. Quantum computing, for example, leverages superposition and entanglement to explore multiple computational paths simultaneously. Whether we frame this as collapsing probabilities, Copenhagen, or parallel explorations in multiple branches, many worlds, the practical result is the same. Quantum systems can process information in ways classical computers cannot. The philosophical implications are profound. Copenhagen suggests a participatory universe where consciousness and measurement shape reality. Many worlds suggest a reality of infinite possibilities, where each choice creates a branching path through the multiverse. Both views encourage us to reconsider our role as observers, participants, and co-creators of the world we experience. Meditatively, we can reflect on the poetic nature of these ideas. Consider the gentle act of observing a leaf drifting on a stream. Your attention does not just passively record its motion. In a subtle, metaphorical sense, your awareness interacts with the unfolding patterns of reality. At the quantum scale, this interaction becomes mathematically precise. Observation is not passive. It is a creative engagement with potentialities. Even in the many worlds view, the universe invites contemplation. Each choice, each interaction, spawns countless realities, some very similar to ours, others radically different. Your awareness traverses one path, yet the universe hums with infinite parallel possibilities, a gentle reminder of both freedom and connection. Each moment is a doorway into myriad potential experiences, each a reflection of the universe's playful, probabilistic nature. Finally, Consider the elegance of these frameworks. Copenhagen reminds us that reality emerges through observation, while many worlds reminds us that all possibilities are real in some branch of existence. Both challenge classical certainty, offering not confusion, but a gentle expansion of perspective. The universe is richer, more mysterious, and more beautiful than we ever imagined. As we close this chapter, take a slow, deep breath, imagining yourself as a participant in this vast quantum dance. Feel the subtle ripples of superpositions, entanglements, and branching realities flowing around and within you. Reality is not fixed. It is a living participatory web of potential, observation, and infinite possibilities. If you have enjoyed exploring the Copenhagen interpretation, many worlds, and the profound role of observation, consider subscribing to Sleep Entangled. By joining this journey, you help create more immersive, soothing explorations where science and serenity meet, allowing us to uncover the poetic truths of the universe together. Chapter 7: Quantum Field Theory, the Standard Model, and the Higgs Field. As we move deeper into the quantum realm, we encounter an elegant and transformative perspective: quantum field theory, QFT. Unlike classical physics, which treats particles as isolated objects, QFT views the universe as a vast network of fields, each permeating all of space. Particles, then, are excitations or ripples in these fields, much like waves rising in a calm ocean. This framework reshapes our understanding of matter, energy, and the dynamic fabric of reality itself. Imagine a calm, still lake. A stone dropped into the water creates ripples that spread outward. In quantum field theory, these ripples are particles, appearing as localized disturbances in the underlying field. The electron is a ripple in its electron field. Photons are ripples in the electromagnetic field, and so forth. In this sense, reality is not composed of solid and discrete objects, but vibrating interconnected waves of energy. QFT provides a unified framework to describe how particles interact, encompassing the forces of nature: electromagnetism, the weak nuclear force, and the strong nuclear force. Gravity remains a challenge within this framework, a puzzle that continues to inspire physicists seeking a unified theory. Yet within its domain, QFT is both beautifully predictive and profoundly insightful, explaining the behavior of matter at the smallest scales. Central to this understanding is the Standard Model of particle physics, a catalog of the fundamental building blocks of the universe. This model divides matter into quarks and leptons, which make up protons, neutrons, and electrons, and identifies bosons, particles that mediate forces. The photon carries the electromagnetic force, gluons mediate the strong force, and W and Z bosons govern the weak force. Together, these particles form the orchestra of existence, interacting through elegant mathematical symphonies to create everything we observe. Yet one particle stands out for its subtle but crucial role: the Higgs boson, born from the Higgs field. Imagine moving through a thick, invisible molasses. Some particles glide easily, while others are slowed, acquiring what we perceive as mass. The Higgs field is this molasses, and the Higgs boson is the excitation that confirms its existence. Without the Higgs mechanism, particles would be massless, stars would not form, and matter as we know it would not exist. This field is a quiet sculptor of reality, shaping the very substance of the cosmos. QFT also reframes our understanding of empty space. The quantum vacuum, far from being inert, is alive with fluctuations, a seething landscape where virtual particles spontaneously emerge and vanish. These ephemeral particles influence real phenomena, from the Casimir effect to subtle contributions to particle masses and interactions. The universe, even at its emptiest points, is dynamic, pulsing with potential and gentle energy. An elegant aspect of QFT is its ability to unify interactions and predict phenomena with astounding accuracy. For example, quantum electrodynamics, QED, a subset of QFT, describes the interactions between light and matter with precision unmatched in the history of science. Richard Feynman's diagrams provide a visual language to track particle interactions, turning abstract equations into intuitive, almost poetic representations of reality in motion. Despite its successes, the standard model is incomplete. Gravity, described by Einstein's general relativity, does not yet fit naturally into the quantum framework, and phenomena like dark matter and dark energy remain mysterious. Yet this incompleteness is not a limitation. It is an invitation, a gentle nudge from the universe, encouraging exploration, curiosity, and wonder. The pursuit of a theory of everything continues to inspire generations of physicists, a reminder that science is as much about questions as it is about answers. QFT also introduces the concept of quantum fields as active participants in reality rather than passive backdrops. Fields mediate forces, enable interactions, and shape the probability landscapes in which particles move. In this view, the universe is not a collection of isolated objects, but a dynamic, interconnected web where observation, interaction, and the underlying fields together generate the phenomena we perceive. This perspective has practical applications as well. High-energy particle colliders, like the Large Hadron Collider, probe these fields, smashing particles together to reveal their inner structure. Through these experiments, we witness the subtle dance of energy and matter, the quantum tapestry from which reality is woven. The discovery of the Higgs boson in 2012 was a triumph of this approach, confirming the mechanism that endows particles with mass and demonstrating the predictive power of quantum field theory. Quantum fields also provide a framework to explore the probabilistic nature of reality. The wave function, central to earlier chapters, emerges naturally from QFT as a description of field excitations. Uncertainty, superposition, and entanglement are not anomalies. They are intrinsic properties of a universe composed of fields and probabilities where observation, interaction, and context shape outcomes. To bring this closer to our meditative reflection, imagine the universe as a calm, flowing ocean. Each wave is a particle, each ripple a quantum fluctuation, and each interaction a gentle collision that shapes the pattern of the waves. Observation does not merely record this flow, it participates in it, nudging the waves into particular forms, while the ocean beneath hums with infinite possibilities. Consider, too, the elegance of the Higgs mechanism. Particles acquire mass not by intrinsic property, but by interacting with a field that permeates space. This subtle, invisible interaction shapes the universe profoundly. Stars, planets, and life itself depend on it. It is a quiet reminder that reality is often sculpted not by the obvious or dramatic, but by gentle, persistent, underlying structures. As we reflect on quantum field theory, the Standard Model, and the Higgs field, a pattern emerges. The universe is dynamic, participatory, and profoundly interconnected. From the tiniest quark to the vast network of fields, reality is a flowing, interacting tapestry, responsive to observation, interaction, and subtle probabilistic influences. It is a universe that invites wonder, reflection, and gentle curiosity. In the context of our exploration, QFT encourages us to consider the poetic metaphor. Just as fields shape particles, our awareness shapes perception. Interaction, observation, and subtle influence ripple outward, affecting the flow of possibilities around us. The universe is not merely a stage, but an active participant in its own unfolding, inviting us to witness, reflect, and engage with the subtle elegance of existence. Before we close this chapter, take a slow, deep breath. Imagine particles rippling through invisible fields, fluctuations dancing in the vacuum, and forces interacting gracefully across space. Feel the subtle, quiet rhythm of reality, a gentle reminder that the universe is alive with potential, interaction, and interconnectedness. If you have enjoyed this journey through quantum field theory, the Standard Model, and the Higgs field, consider subscribing to Sleep Entangled. By joining, you support immersive explorations where science meets serenity, and together we uncover the poetic and profound truths of the quantum universe. Chapter 8: Quantum Electrodynamics, Feynman Diagrams, and the Dance of Light and Matter. As we continue our journey through the quantum universe, we arrive at a particularly elegant and deeply revealing framework, quantum electrodynamics, or QED. This theory describes the interaction between light, photons, and matter, charged particles like electrons, with extraordinary precision. It is, in many ways, the crown jewel of quantum field theories, providing insights not only into the subatomic world, but into the very fabric of reality. To appreciate QED, imagine a calm pond at twilight. Toss a pebble in, and ripples radiate outward. Now imagine a second pebble tossed nearby. The ripples intersect, interfere, and dance across the surface. This interplay is a gentle metaphor for the interactions between light and matter. Photons, like the ripples, traverse space, influencing electrons and being influenced in return. QED captures this intricate dance, mathematically describing how particles exchange energy and momentum through light. Historically, the development of QED marked a revolution in physics. Classical electromagnetism, formulated by Maxwell, described how charged particles generate and respond to electric and magnetic fields, yet it could not explain phenomena such as the anomalous magnetic moment of the electron or the precise scattering of photons off electrons. QED emerged to fill this gap, blending quantum mechanics with special relativity and revealing a universe where light and matter interact in subtle, probabilistic, and beautifully intricate ways. One of the most transformative contributions to QED came from Richard Feynman, who introduced Feynman diagrams. These diagrams are not merely illustrations, they are tools for calculation, visualization, and intuition. Each line, vertex, and curve represents a real aspect of particle interaction. Straight lines for particles, wavy lines for photons, and points where they meet for interactions. Through these diagrams, even the most complex quantum processes become understandable and approachable, revealing a universe that is simultaneously rigorous, elegant, and playful. Consider a photon scattering off an electron, a process known as Compton scattering. Feynman diagrams allow us to trace the photon's path, accounting for all possible ways the interaction could occur. Each path contributes to the final probability, illustrating the essential role of superposition in real-world phenomena. Here, quantum mechanics ceases to be abstract and becomes its tool to describe tangible, measurable reality. QED also demonstrates the profound concept of virtual particles. In the vacuum, fleeting particle-antiparticle pairs emerge and vanish, mediating forces and subtly shaping interactions. Although invisible and ephemeral, these virtual entities leave measurable effects, such as the Casimir effect, where two plates in a vacuum experience an attractive force due to quantum fluctuations. In this sense, the vacuum is not empty, but alive with potential, a stage for the ceaseless dance of light and matter. The predictive power of QED is astounding. Calculations of phenomena like the electron's magnetic moment match experimental results to 12 decimal places, a level of precision almost unfathomable in any other branch of physics. This accuracy transforms our understanding from philosophical speculation to empirical certainty, grounding the poetic elegance of quantum mechanics in measurable, observable effects. Beyond pure physics, QED has profound philosophical implications. It challenges our classical intuition about cause and effect. When a photon interacts with an electron, it is not simply following a single path. Instead, all possible paths contribute, and the resulting behavior emerges as a sum of probabilities. Reality at this level is a web of potentialities, where certainty is emergent, not fundamental. To visualize this, imagine walking through a forest. You see a path winding through the trees, but there are countless potential trails hidden in the undergrowth. The path you follow emerges not by dismissing the other trails, but by interacting with the terrain and gently navigating the possibilities. In the quantum world, this interaction is governed by the mathematics of QED, where the forest is the vacuum. The trails are possible particle paths, and the walker is the observer or the system itself. Feynman's diagrams also provide a profound insight into the unity of interactions. Whether it is light scattering off an electron, electron-positron annihilation, or more exotic processes, the same mathematical principles govern the dynamics. This universality reflects a deep symmetry in nature, suggesting that the diverse phenomena we observe are merely different expressions of the same underlying quantum fabric. QED further demonstrates the role of entanglement and correlation. When photons or electrons interact, they can become entangled, sharing a connection that persists even across vast distances. Measurements on one particle immediately inform us about its partner, a feature Einstein famously called spooky action at a distance. In the context of QED, entanglement is not mysterious. It is a natural consequence of the exchange of quantum fields, revealing a subtle but pervasive interconnectedness throughout the universe. Practically, QED has enabled technologies that shape our everyday lives. Lasers, semiconductors, and quantum optics all rely on the principles of QED. By understanding how light and matter interact at the quantum level, we can design devices that manipulate photons and electrons with extraordinary precision, from medical imaging to secure communications. The dance of light and matter is not confined to thought experiments. It is tangible, usable, and transformative. Meditatively, we can reflect on the poetic nature of QED. Each photon's journey is a gentle ripple, each electron's movement a soft pulse, and the vacuum itself a subtle hum of potential. Observation, measurement, and interaction are not passive acts. They are participatory engagements with the universe, co-creating the reality we perceive. The mathematics is rigorous, yet the experience is poetic, a reminder that science and wonder are intertwined. The elegance of QED also offers insight into the limits and possibilities of human knowledge. While the equations are precise, the underlying processes remind us that reality is fundamentally probabilistic and that certainty emerges from the interplay of possibilities. This invites a gentle humility. The universe is far richer, subtler, and more playful than our classical intuitions might suggest. Embracing this uncertainty is not a weakness. It is a doorway to curiosity, awe, and profound engagement with reality. As we approach the end of this chapter, let us take a moment to reflect on the dance of light and matter. Picture photons weaving through space, electrons gliding along field lines, and the vacuum pulsating with virtual particles. Feel the rhythm, the subtle interactions, and the beauty of a universe that is both precise and mysterious, measurable and poetic. In this dance, we are observers, participants, and witnesses, gently navigating the infinite possibilities of existence. If you have enjoyed exploring quantum electrodynamics, Feynman diagrams, and the dance of light and matter, consider subscribing to Sleep Entangled. By joining, you help create more immersive, soothing journeys where science meets serenity, and together we continue to uncover the poetic truths of the quantum universe. Chapter 9: Quantum Computing, Decoherence, and Quantum Biology. As we journey further into the quantum universe, we arrive at a realm where the abstract beauty of quantum mechanics meets tangible, transformative technology, and even the subtle processes of life itself. This chapter explores the frontiers of quantum computing, the challenges of decoherence, and the emerging field of quantum biology. Together, these topics reveal a universe that is not only probabilistic, but profoundly interconnected, where observation, interaction, and quantum effects shape both technology and life. Let us begin with quantum computing, a field that transforms the conceptual principles of superposition and entanglement into practical computational power. Unlike classical computers, which encode information as bits, zeros, and ones, quantum computers use qubits, which can exist in multiple states simultaneously. This property of superposition allows quantum computers to perform complex calculations in parallel, dramatically accelerating tasks such as factorization, optimization, and simulation of quantum systems. Imagine a vast library with billions of books. A classical computer reads each book one by one, slowly and methodically. A quantum computer, however, can explore all possible books simultaneously, assessing probabilities and extracting solutions with efficiency that seems almost magical. It is a manifestation of quantum principles in a technology that could reshape everything from cryptography to medicine. Yet building a quantum computer is far from trivial. Qubits are delicate, easily disturbed by environmental interactions. This phenomenon, known as decoherence, disrupts superposition and entanglement, collapsing quantum states into classical outcomes. Maintaining coherence requires extreme conditions, often near absolute zero, where thermal vibrations and external noise are minimized. Researchers carefully shield qubits using superconducting circuits, trapped ions, or topological states to preserve their fragile quantum properties. Decoherence also illustrates a profound insight into quantum reality. It shows that quantum systems are inextricably linked to their environment, and that observation, even unintended, shapes outcomes. This mirrors earlier discussions on wave function collapse and the observer effect, reminding us that the line between quantum and classical reality is delicately maintained, and that the universe itself is a participatory dance of potentialities. Quantum computing is not only a technological marvel, but also a philosophical window. Superposition allows qubits to explore multiple paths simultaneously, while entanglement ensures that their states remain interconnected regardless of distance. In this sense, quantum computers echo the underlying interconnectedness of reality itself, offering both practical applications and poetic metaphors for the universe's structure. Beyond computers, quantum mechanics even appears to influence life itself, a field now emerging as quantum biology. Consider birds navigating vast distances during migration. Evidence suggests that some species use quantum entanglement in their retinal proteins to sense Earth's magnetic field, a subtle quantum effect guiding them across continents. Similarly, plants exploit quantum coherence in photosynthesis, allowing energy to traverse molecular networks with extraordinary efficiency, far surpassing what classical physics would predict. These examples reveal that life may not merely obey quantum rules, it may actively leverage them. Quantum effects, once thought limited to subatomic particles, may contribute to macroscopic biological processes, from enzyme reactions to the efficiency of vision. The universe, it seems, is creative in harnessing the subtle powers of probability, entanglement, and superposition, applying them not only to particles, but to the intricate dance of living systems. Quantum biology also raises questions about consciousness and perception. If living systems can exploit quantum mechanics, might the brain itself use subtle quantum effects to process information? While speculative, research in this area hints at possibilities: coherence in neuronal microtubules, quantum tunneling in neurotransmitter reactions, and entanglement-like phenomena that could, in principle, enhance cognitive processes. This does not imply mysticism, but invites wonder at the potential reach of quantum principles into everyday life. Returning to decoherence, we see its relevance both in technology and in biology. In quantum computers, decoherence is a challenge to be mitigated. In living systems, decoherence is managed by evolution, allowing life to harness quantum effects without losing stability. The universe, in this sense, balances the delicate interplay between order and uncertainty, classical behavior, and quantum richness, providing a framework for both stability and innovation. One of the most intriguing aspects of quantum computing is the quantum speedup, the ability to solve certain problems exponentially faster than classical computers. This is particularly relevant for fields like quantum chemistry, where simulating molecular interactions requires accounting for superpositions of quantum states. Traditional computers struggle with the combinatorial explosion of possibilities, but quantum machines can naturally explore these superpositions, predicting molecular behavior with unprecedented efficiency. This could revolutionize drug discovery, materials science, and the understanding of complex biological systems. Quantum algorithms, such as Shor's algorithm for factoring large numbers, leverage entanglement and interference to achieve results impossible for classical machines in reasonable time frames. Similarly, Grover's algorithm optimizes search problems by exploring multiple paths simultaneously, illustrating the profound ways quantum principles translate into computational power. These examples show that the abstract principles we have been exploring, superposition, entanglement, and probability, have concrete, even transformative applications in our world. Meditatively, we can reflect on the poetic implications. Imagine a qubit as a gentle ripple in a calm pond, existing in multiple states at once. Decoherence is the inevitable interaction with the surrounding water, collapsing possibilities into a particular pattern. Yet nature has found ways to navigate, leverage, and even embrace this interaction, both in technology and in life. Observation, interaction, and subtle environmental influence shape outcomes, reinforcing the idea that participation is fundamental to reality. The field of quantum biology also encourages humility and curiosity. Life has evolved to exploit the probabilistic nature of the universe, suggesting that evolution itself may be a quantum-informed process. The interconnectedness of systems, the efficiency of energy transfer, and the subtle use of coherence in biological networks all hint at a universe where quantum principles are not confined to laboratories but are woven into existence itself. As we close this chapter, take a slow, deep breath. Imagine qubits floating in superposition, particles entangled across space, and photons guiding life in ways both subtle and profound. Feel the rhythm of decoherence, the gentle collapse of possibilities, and the intricate dance that allows technology and biology alike to harness the quantum fabric of reality. The universe is alive with potential, interconnectedness, and playful complexity, inviting reflection, wonder, and gentle curiosity. If you have enjoyed exploring quantum computing, decoherence, and quantum biology, consider subscribing to Sleep Entangled. By joining, you help support immersive, soothing explorations where science meets serenity, and together we continue to uncover the poetic and profound truths of the quantum universe. Chapter 10: Delayed Choice Experiments, Quantum Eraser, and Retrocausality. As we continue our journey through the quantum landscape, we enter a domain where the nature of time, observation, and causality itself begins to blur. The world of delayed choice experiments, the quantum eraser, and retrocausality. These concepts challenge not only classical physics, but also our deepest intuitions about how the universe unfolds. They invite us to reconsider what it means for events to be fixed, what it means to observe, and even how the past, present, and future may be intertwined. The story begins with a question that seems almost paradoxical. Can the future influence the past? In classical physics, the answer is a resounding no, because always precedes effect, and events are strictly ordered. But quantum mechanics, with its probabilistic nature and superpositions, opens the door to phenomena that challenge this linear perspective. Delayed choice experiments, first proposed by physicist John Archibald Wheeler, are a striking example. Imagine a photon traveling toward a double-slit apparatus where it can pass through two slits simultaneously, behaving like a wave and creating an interference pattern. In a delayed choice experiment, The decision to observe which slit the photon goes through is made after the photon has already entered the apparatus. Remarkably, the results show that the photon's earlier behavior, whether it acted as a particle or a wave, depends on a measurement made later in time. It's as if the photon knew the future observation and its past behavior adjusted accordingly. This counterintuitive result is both humbling and exhilarating. It suggests that reality at the quantum level is not fixed in a classical sense, but is fluid, contingent, and profoundly linked to observation. Time, as we perceive it, may be less a rigid arrow and more a flexible thread, woven together by the act of measurement and interaction. The quantum eraser experiment takes this idea even further. In this variation, which path information, the knowledge of which slit the photon went through, can be erased after the photon has been detected. When this information is erased, the interference pattern reappears, as though the photon's wave-like behavior had never been collapsed. The experiment demonstrates that reality is not merely observed. It is interactively constructed, with measurement choices influencing outcomes in ways that challenge classical notions of causality. Retrocausality, the philosophical interpretation of these experiments, suggests that effects may influence causes in subtle, probabilistic ways. This does not imply macroscopic time travel or paradoxical scenarios in our everyday lives, but it does hint at a non-linear, deeply interconnected structure to quantum events. In this framework, the universe is a tapestry where the threads of past, present, and future are interwoven, and observation plays a central role in defining which patterns emerge. Meditatively, we can imagine this as a dance of possibilities. Each quantum particle moves like a dancer, poised between multiple positions, each step influenced not only by prior movements, but by the subtle instructions provided by future measurements. Observation is the rhythm, decoherence is the guidance, and reality itself is the performance that unfolds through participation. It is a gentle reminder that the universe is both playful and precise, mysterious and ordered. The implications extend beyond photons and particles. Consider entangled systems, where two particles share a connection across space. If we perform a delayed choice measurement on one particle, the correlated outcomes of its partner reflect a retroactive adjustment. The universe, in this sense, is responsive, relational, and profoundly interconnected, weaving the fabric of reality through observation, interaction, and coherence. Quantum eraser and delayed choice experiments also have profound philosophical and practical resonance. They highlight the limits of classical intuition and the importance of embracing uncertainty, superposition, and interdependence. In a gentle, meditative sense, they remind us that our understanding of cause and effect is contingent, that certainty is emergent, and participation is essential. The universe does not simply happen to us. We are engaged in a continuous dialogue with it. This dialogue is mirrored in the macroscopic world, albeit in subtler ways. Biological systems, as we explored in the previous chapter, exploit coherence, entanglement, and superposition in ways that enhance efficiency and adaptability. While retrocausality at a macroscopic scale remains speculative, the very fact that quantum processes permeate living systems hints at a world where the boundaries between cause and effect, past and future, are more nuanced than our classical perceptions suggest. Practically, These experiments have inspired new quantum technologies. Quantum communication, secure encryption, and emerging protocols for quantum networks rely on entanglement, measurement choices, and the probabilistic nature of outcomes. The principles illustrated by delayed choice and quantum eraser experiments guide us in designing systems that exploit quantum behavior while navigating its inherent unpredictability. In this way, the philosophical insights of quantum mechanics are translated into concrete technological innovation, bridging abstract wonder with tangible application. Meditatively, we can also reflect on the implications for consciousness and awareness. If observation plays a central role in determining quantum outcomes, then the act of witnessing, of paying attention, is itself a participatory engagement with the universe. Our awareness is not passive. It co-creates reality in subtle, probabilistic, and profoundly interconnected ways. Each measurement, each observation, each act of perception is a gentle shaping of possibilities, guiding the dance of existence itself. Let us consider a moment of personal reflection. Imagine observing a sunset, noticing the colors, feeling the warmth of fading sunlight, and sensing the subtle shifts in the breeze. In a meditative, quantum-inspired perspective, your observation does more than passively record reality. It participates in the unfolding of possibilities. Just as photons respond to delayed measurements in a laboratory, the world around us may respond in its own complex way to our awareness and attention. It is not mystical thinking. It is a poetic analogy rooted in the subtle interplay of probability, observation, and relational interaction that quantum mechanics reveals. The elegance of these experiments lies in their combination of rigorous mathematics and poetic intuition. They invite us to hold complexity and simplicity together, to accept that reality is both probabilistic and structured, unpredictable yet patterned, mysterious yet deeply knowable through careful observation and reflection. They remind us that science is not just a set of facts, but a lens for wonder, inviting curiosity, humility, and engagement with the cosmos. As we bring this chapter to a gentle close, imagine a world where past, present, and future are threads of a single tapestry, where the act of observation weaves the patterns that emerge. Picture photons dancing through slits, wave functions collapsing, and a Rauscher restoring interference, all in a cosmic interplay that is as precise as it is playful. In this delicate balance, we are participants, witnesses, and co-creators, exploring a universe that is simultaneously logical, beautiful, and profoundly mysterious. If you have enjoyed exploring delayed choice experiments, quantum eraser, and retrocausality, consider subscribing to Sleep Entangled. By joining, you help support immersive, soothing journeys where science meets serenity, and together we continue uncovering the poetic truths of the quantum universe. Chapter 11: Quantum Randomness, Uncertainty, and the Nature of Reality. As we venture deeper into the quantum realm, we encounter one of its most profound and humbling aspects: randomness and uncertainty. Classical physics gave us a world of predictable laws, where the trajectory of a planet or the fall of an apple could be calculated with certainty. Quantum mechanics, however, introduces a universe governed by probabilities rather than certainties, where the act of observation, measurement, and interaction fundamentally shapes outcomes. At the heart of this discussion lies Heisenberg's uncertainty principle, a cornerstone of quantum theory. This principle tells us that certain pairs of physical properties, such as a particle's position and momentum, cannot be precisely measured simultaneously. The more accurately we know one, the less precisely we can know the other. This is not a limitation of our instruments, but a fundamental feature of reality itself. At the quantum level, uncertainty is intrinsic, woven into the very fabric of existence. Imagine trying to track a single droplet in a stormy river. As you focus on its exact position, its velocity becomes blurred, shifting unpredictably. Conversely, if you measure its speed precisely, its exact location becomes fuzzy. This interplay is not a flaw, but a delicate balance of possibilities, reflecting the inherent freedom and flexibility of the quantum world. This uncertainty is closely linked with quantum randomness. Unlike classical randomness, which stems from ignorance of all variables, quantum randomness is irreducible. Even with complete knowledge of a system, certain outcomes cannot be predicted deterministically. They emerge probabilistically. A photon encountering a beam splitter, for example, has a probability of being reflected or transmitted, but no hidden variable determines the outcome in advance. One of the most striking implications of quantum randomness is that reality is not preordained. While we may perceive the world as stable and predictable, at the microscopic level, the universe continuously explores multiple possibilities simultaneously, collapsing into specific outcomes only when observed. This perspective reshapes our understanding of causality, chance, and the emergence of order. Superposition, a concept we have encountered before, is intimately connected to this randomness. A particle can exist in multiple states at once, a cloud of probabilities, until measurement collapses it into a single outcome. Schrödinger's famous cat thought experiment elegantly illustrates this. The cat is both alive and dead in a superposed state until observation determines its fate. This is not a macabre joke, but a metaphor for the probabilistic nature of reality itself. Randomness and uncertainty are also vital in quantum technologies. Quantum random number generators, for instance, exploit intrinsic quantum randomness to produce sequences that are fundamentally unpredictable. These have applications in secure encryption, simulations, and even gambling, providing true randomness in a world where classical methods can only approximate it. Yet quantum uncertainty is not a limitation. It is a source of creativity and novelty in the universe. Without uncertainty, the richness and diversity of the cosmos, from the formation of galaxies to the emergence of life, would be impossible. Randomness allows particles to explore multiple possibilities, enabling evolution, complexity, and innovation. In this sense, uncertainty is both liberating and essential, offering a canvas upon which the universe paints its infinite variations. This probabilistic nature also invites a more reflective, meditative perspective. Consider the act of making a choice. While macroscopic decisions are influenced by myriad factors, at the deepest levels, uncertainty is embedded in existence itself. Life unfolds in a landscape of possibilities, some determined, some open, inviting curiosity, awareness, and thoughtful engagement. The universe is not a rigid script, but a collaborative performance, with participants, conscious or otherwise, shaping outcomes in subtle ways. Another remarkable manifestation of quantum randomness is quantum tunneling, where particles traverse barriers that classical physics says they cannot. This phenomenon is essential for processes like radioactive decay, nuclear fusion in stars, and even some biochemical reactions. Tunneling exemplifies how randomness at the quantum level can produce macroscopic consequences, powering the sun, enabling life, and sustaining the cosmos in ways that are simultaneously elegant and unpredictable. In a meditative visualization, imagine the quantum world as a gently rippling sea, where each wave represents a probability. Particles surf these waves, exploring countless paths simultaneously. Observation acts as a gentle hand, collapsing the waves into a single ripple, shaping the outcome while preserving the underlying beauty and complexity of the quantum ocean. Each measurement is an invitation to witness, participate, and engage with the profound subtleties of existence. Quantum randomness also challenges our notions of determinism and predictability. In classical mechanics, knowing the initial conditions of a system allows complete prediction of its future behavior. In quantum mechanics, however, even perfect knowledge does not yield certainty, only probabilities. This shift from determinism to probabilism has philosophical, practical, and poetic implications, reminding us that embracing uncertainty is both necessary and enriching. Even at macroscopic scales, these principles can manifest in subtle ways. For example, biological systems appear to exploit probabilistic processes, as we explored in quantum biology. Photosynthesis, bird navigation, and enzyme dynamics may leverage quantum superposition and tunneling, suggesting that life itself has learned to dance with uncertainty. The universe, in turn, is not a rigid mechanism, but a dynamic, probabilistic tapestry where randomness contributes to resilience, adaptability, and creativity. Furthermore, experiments like the delayed choice quantum eraser highlight how probabilities, observation, and measurement intertwine with time itself. These experiments reinforce that the universe is not a passive backdrop, but an active, responsive entity, where uncertainty, randomness, and observation together shape the unfolding of reality. Each photon, electron, or atom navigates a landscape of possibilities, ultimately contributing to the cosmic symphony that is life, matter, and consciousness. Randomness, far from being chaotic, is structured, relational, and meaningful at a deep level. Quantum field theory, which describes particles as excitations setting in underlying fields, emphasizes that fluctuations, probabilities, and interactions are fundamental to the universe's architecture. Energy is not static, particles are not fixed, and reality itself is vibrant, dynamic, and alive with potential. Meditatively, consider your own awareness. Thoughts, choices, and perceptions emerge in a landscape of possibilities, influenced by prior experience, context, and subtle interactions. Just as a particle collapses into a state upon observation, our conscious attention shapes the unfolding of experience, not deterministically, but probabilistically. This analogy does not imply mysticism, but invites gentle reflection on our participatory role in reality. As we draw this chapter to a close, take a moment to breathe deeply. Imagine the waves of probability, the dance of particles, and the gentle collapse of possibilities through observation. Feel the richness of uncertainty, the elegance of randomness, and the beauty of a universe that is simultaneously unpredictable, structured, and profoundly interconnected. Embrace the wonder, humility, and curiosity that quantum mechanics invites, knowing that your awareness is part of this cosmic interplay. If you have enjoyed exploring quantum randomness, uncertainty, and the nature of reality, consider subscribing to Sleep Entangled. By joining, you help support immersive, soothing journeys where science meets serenity, and together we continue to uncover the poetic and profound truths of the quantum universe. Chapter 12: Embracing Quantum Uncertainty, Reflection and Connection. As we arrive at the final stretch of our journey through the quantum landscape, it's time to step back and reflect on what we have discovered. From the dual nature of light to the entangled connections spanning the cosmos, from delayed choice experiments to the gentle unpredictability of quantum randomness, the universe reveals itself as both deeply mysterious and beautifully coherent. In this chapter, we explore how embracing quantum uncertainty can inform not only our understanding of physics, but also our perception of life, consciousness, and connection. We will gently examine how the principles we have explored can inspire reflection, mindfulness, and a sense of participation in the vast, probabilistic tapestry of existence. Quantum mechanics has taught us that certainty is an emergent property, not an absolute condition. Particles do not exist in fixed states, independent of observation. Instead, they inhabit a spectrum of possibilities, a cloud of potential that collapses into reality through interaction and measurement. In our own lives, we can view our experiences in a similar light. Circumstances, thoughts, and emotions are not predetermined or fixed. They unfold through a combination of influences, choices, and chance. This understanding invites curiosity, patience, and gentle acceptance. Consider the metaphor of a river flowing through a landscape of possibilities. The water does not move along a single predetermined path. It meanders, eddies, and shifts, exploring multiple routes before converging into observable streams. Life, in many ways, mirrors this process. Our choices, interactions, and observations guide the river of our experience, shaping reality without strictly determining it. Just as quantum particles explore a landscape of probabilities before measurement, we navigate a landscape of possibilities with attention, intention, and openness. One of the most profound lessons of quantum mechanics is the interconnectedness of all things. Entangled particles, separated by vast distances, maintain correlations that defy classical intuitions about space and communication. The universe is not a collection of isolated entities. It is a web of relationships where each part is subtly linked to every other part. Meditatively, we can reflect on our own lives and relationships in this context. Our awareness, actions, and connections ripple through the fabric of existence, shaping outcomes in ways we may not immediately perceive. Embracing uncertainty also encourages humility and wonder. Classical physics often fosters a sense of control, where precise measurement and calculation lead to predictable outcomes. Quantum mechanics, in contrast, reminds us that the universe is fundamentally probabilistic, that outcomes emerge from a dynamic interplay of possibilities and observation. This perspective is not disempowering. It is liberating, opening space for creativity, exploration, and gratitude for the unfolding mystery of existence. Let us reflect on superposition, the principle that particles can exist in multiple states simultaneously until measured. This principle offers a gentle analogy for human experience. Our potential is vast, multifaceted, and rich with possibility. Decisions, thoughts, and actions represent moments of observation collapsing certain potentials into reality while leaving others unexplored. Recognizing this invites mindful awareness, encouraging us to engage with life intentionally while honoring the infinite potential that exists in each moment. Quantum entanglement, too, offers a poetic lens for reflection. When two particles become entangled, the state of one instantaneously influences the other, regardless of distance. In human terms, this can be seen as a metaphor for the profound connections that weave through our lives. Our interactions, words, and intentions resonate beyond immediate perception, subtly shaping the experiences of others. Understanding this interconnectedness fosters empathy, compassion, and a sense of unity with the world around us. Decoherence, the process by which quantum superpositions transition to classical certainty, offers another perspective. Just as environmental interactions collapse quantum possibilities into observable states, our interactions, habits, and experiences shape our personal reality. Mindful engagement allows us to participate consciously in this process, guiding outcomes while respecting the inherent unpredictability of existence. In essence, we become co-creators of our lived experience, dancing with uncertainty rather than resisting it. The delayed choice and quantum eraser experiments remind us that observation is active and participatory, not merely passive. This principle extends to our perception of life. Each moment of awareness, whether it is noticing a sunset, listening to a friend, or contemplating a thought, shapes our experience. Our attention is a tool for co-creation, influencing the unfolding of reality in subtle but meaningful ways. This perspective encourages presence, mindfulness, and gentle curiosity. Quantum randomness further illustrates that the universe is not rigid or deterministic. Outcomes are probabilistic, not predetermined, and unpredictability is an intrinsic feature of reality. In life, this mirrors the countless variables and possibilities that shape our paths. Embracing uncertainty fosters resilience, adaptability, and openness, allowing us to navigate life with grace and wonder rather than anxiety or control. Let us also reflect on quantum field theory, which portrays particles as excitations in underlying fields. This elegant framework emphasizes the dynamic, interconnected nature of the universe. Space is not empty. It is alive with energy, fluctuations, and potential. In our own experience, we can perceive life similarly, not as isolated events or entities, but as a network of influences, relationships, and possibilities, each moment vibrant with latent potential. Meditatively, you might imagine yourself as a particle in this quantum field, exploring multiple paths, entangled with others, influenced by observation, and participating in the unfolding of reality. Your consciousness is both observer and participant, navigating a rich landscape of uncertainty, connection, and emergent order. Each thought, choice, and observation contributes to the tapestry of existence, highlighting the beauty, complexity, and interconnectedness of life. Embracing quantum uncertainty also invites creative engagement with the world. Just as quantum systems explore multiple possibilities before measurement, we can explore multiple approaches, perspectives, and ideas before settling on action. This encourages experimentation, innovation, and playful curiosity, turning uncertainty from a source of fear into a space for growth, exploration, and discovery. Finally, let us consider the poetic resonance of quantum mechanics. In concepts such as superposition entanglement, and decoherence are not just abstract mathematical tools, they are metaphors for presence, connection, and participation. Reality, like a wave function, contains a multitude of possibilities, collapsing into form through engagement, observation, and choice. By reflecting on these principles, we cultivate mindfulness, wonder, and a sense of co-creative presence in our lives. As we gently conclude this final chapter, take a moment to breathe deeply. Imagine the waves of probability, the delicate collapse of possibilities, and the intricate web of entangled connections. Feel the freedom, curiosity, and interconnectedness that quantum mechanics invites. Recognize your role as a participant, observer, and co-creator in this vast probabilistic universe. If you have enjoyed exploring embracing quantum uncertainty, reflection, and connection, consider subscribing to Sleep Entangled. By joining, you help support immersive, soothing journeys where science meets serenity, and together we continue uncovering the poetic and profound truths of the quantum universe. Closing reflection. As we draw our journey through the quantum universe to a gentle close, let us pause for a moment and simply breathe. Imagine the countless particles, waves, and probabilities that form the foundations of reality. Imagine their delicate dance across space as in time, their endless superpositions and entanglements, their interactions that ripple across the cosmos in ways both subtle and profound. This universe, at once mysterious and accessible, invites you not only to observe, but to participate, reflect, and wonder. Throughout this journey, we have explored some of the most fascinating ideas in modern physics. We began with wave-particle duality, discovering that light and matter are both waves and particles, depending on how we observe them. We delved into superposition, where particles exist in multiple states simultaneously, until observation collapses them into a single reality. We ventured into entanglement, witnessing connections that span space and time, and reflected on quantum randomness, where uncertainty is not a limitation, but a fundamental feature of existence. Each of these concepts reshapes not only our scientific understanding, but also the way we perceive our own participation in reality. In the quantum world, observation is not passive, it is an act of engagement. Similarly, in our lives, awareness shapes experience. Every thought, every choice, every moment of presence, and contributes to the unfolding tapestry of existence. Reality is co-created, not fixed, and each of us is both observer and participant. Let us consider decoherence, the process that allows quantum superpositions to transition into classical certainty. This principle mirrors our own experience. Interactions with our environment, choices we make, and habits we develop gradually shape our lived reality. Just as decoherence does not destroy the underlying quantum nature, but guides it into observable outcomes, our awareness can gently guide possibilities into experience, honoring the beauty of uncertainty while allowing for coherence in our lives. The delayed choice and quantum eraser experiments invite us to reflect on time and causality. These experiments suggest that events are not always strictly linear, and that observation can influence outcomes even retroactively. In life, this reminds us that our understanding of cause and effect is sometimes limited, and that perspective, timing, and reflection matter as much as action. The universe, it seems, encourages us to explore, question, and engage thoughtfully with the flow of time and events. Quantum mechanics also challenges are classical notions of determinism. Randomness at the quantum level is not a flaw. It is a feature, a source of creativity, flexibility, and novelty. Life, much like the quantum world, thrives in uncertainty and possibility. By embracing unpredictability, we open ourselves to new experiences, discoveries, and insights. We cultivate resilience, curiosity, and a sense of playful engagement with existence. Reflect for a moment on quantum entanglement. Two particles, though separated by vast distances, maintain a connection that defies classical intuition. In our own lives, this can serve as a gentle reminder of interconnectedness. Our thoughts, words, and actions reverberate through networks of relationships, sometimes imperceptibly, yet profoundly. Compassion, awareness, and kindness are ways we honor this entanglement, contributing to a world where our influence stretches beyond immediate perception. The quantum vacuum, alive with fluctuations and potential, is another beautiful metaphor. It is not empty, but brimming with energy and possibility. Similarly, the spaces in our lives, the quiet moments, the pauses between events, are full of potential. They offer the opportunity for reflection, insight, and creativity. In stillness, we can sense the subtle currents that shape experience, just as physicists explore the vibrant energy fields that underpin reality. Consider also quantum tunneling, the phenomenon where particles traverse barriers without the classical energy required. This reminds us that even the seemingly impossible may have a path, even if it is probabilistic. In our own journeys, obstacles may not always be as insurmountable as they appear. Possibility exists in ways that transcend rigid expectations, inviting patience, exploration, and gentle courage. Now let us return to the principle of superposition, a cornerstone of quantum mechanics. Just as particles inhabit multiple potential states, we too carry within us countless possibilities. Every decision, every thought, every small action represents an observation, a choice that collapses certain potentials into experience. By recognizing this, we cultivate mindfulness and intentionality, participating consciously in the co-creation of our reality while honoring the richness of possibilities that remain unexplored. Quantum physics also reshapes our understanding of time, causality, and reality itself. The universe is not merely a deterministic machine. It is a dynamic, probabilistic web of interactions, fields, and particles. Understanding this invites humility and wonder as we realize that our knowledge, though powerful, is inherently limited. Yet within this limitation lies freedom, the freedom to explore, to imagine, to wonder, and to participate consciously in the unfolding universe. As we reflect on these concepts, it becomes clear that science and meditation, observation and reflection, theory and lived experience are intertwined. Quantum mechanics is not just an abstract field of mathematics. It is a lens for contemplating life, awareness, and existence. It invites us to approach the universe with curiosity, openness, and a sense of playful exploration. Imagine the universe as a vast, shimmering field of probabilities. Each particle, wave, and interaction is a brushstroke in a grand cosmic painting. Each observation, whether by a physicist or by conscious awareness, gently collapses waves into experience, adding detail, depth, and texture. In this cosmic artwork, you are both observer and participant, contributing to the elegance, unpredictability, and interconnectedness of existence. In the gentle rhythm of your breathing, you might imagine these quantum fields subtly responding to awareness, like ripples across a vast, infinite pond. Each thought, each act of mindfulness, each moment of presence creates resonances that extend far beyond immediate perception. The universe is as alive with possibility, and your awareness is an active participant in its unfolding. As we bring this journey to a close, let us embrace uncertainty, randomness, and interconnectedness not as sources of anxiety, but as invitations to wonder, creativity, and reflection. Life, like the quantum world, is rich, complex, and profoundly beautiful. Every moment holds the potential for discovery, insight, and connection. Now, gently returning your focus inward, take a deep breath and reflect on all that we have explored: wave-particle duality, superposition, entanglement, decoherence, quantum tunneling, the quantum vacuum, randomness, and the participatory role of observation. Let your mind rest in the grace, curiosity, and awe these concepts inspire. Before we part ways, I invite you to take a final moment of mindfulness. Feel the calm, the curiosity, and the gentle wonder that comes from contemplating a universe that is probabilistic, interconnected, and alive with possibility. Allow this reflection to stay with you, quietly enriching your perception, your experience, and your understanding of both the cosmos and yourself. And as we gently conclude this exploration, if you have found peace, curiosity, or inspiration in this journey through quantum mechanics, consider subscribing to Sleep Entangled. By joining, you support immersive, soothing experiences where science meets serenity, helping us create more journeys into the profound and poetic nature of reality. Share your reflections in the comments, let others know what resonated with you, and return whenever you seek calm, insight, or cosmic wonder. Thank you for allowing me to guide you through this quantum journey where particles, probabilities, and possibilities meet conscious awareness. May the subtle mysteries, the elegance of uncertainty, and the beauty of interconnectedness continue to inspire your dreams, your thoughts, and your nightly reflections. Rest gently, breathe deeply, and remember, you are a participant in this vast, mysterious, and profoundly beautiful universe where awareness and curiosity shape reality moment by moment. Good night, and may your dreams carry you softly through the infinite possibilities of existence.